Here's a second example of how to draw an intermolecular forces picture. So remember, in the last slide I said that two polar things mixed together will mix, two nonpolar things will combine, but if you have a polar and a nonpolar thing, then they won't mix. So the first thing you need to do is draw the structures and see if they're both polar, both nonpolar, half and half, like in the previous example or whatever. So in this example, I've got water, which we know now is polar, and will exhibit hydrogen bonding forces, and propane, which has all nonpolar bonds, making it a nonpolar molecule. So it will exhibit London dispersion forces. So these two molecules will not mix. So if they're combined, they're going to form two layers, kind of like when you mix oil and water. So you need to show that the two things are going to stay separate and show the intermolecular forces that you would have in between the molecules, but in two separate layers. So in one layer, you would have the water. So the oxygen and hydrogen would line up, because remember, polar things are going to have partial charges. And when you draw a picture or answer a picture question like this, I also want you to draw more than one molecule. So draw at least two, if not three. So in one layer, you're going to have the water molecules mixing and having hydrogen bonding forces. So make sure you label the forces too. And then in the other layer, you're going to have the propane molecules mixing, and they're going to interact by London dispersion forces. So when you draw the London dispersion forces, there's no partial charges on a nonpolar molecule, so it doesn't matter which atoms you line up. You just need to show the interaction. So that would be a London dispersion force. Okay, so make sure that your answer is complete when you're presented with a question like this. So you will have a couple of these on your test next week. Okay, I've got one more example to show you. Explain the following using molecular structure that should say polarity and intermolecular forces. Why is the boiling point of methanol 64.7 while the boiling point of freon is negative 78? So in other words, why is methanol's boiling point so much higher than freon's? So again, the first thing you want to do is draw out the structures and see, oops, sorry, let me erase that. See what types of intermolecular forces you're going to end up with. Okay. So in a methanol molecule, you do have one side that's nonpolar, so that would have London dispersion forces, and one side that is polar with an OH bond, so that would have hydrogen bonding forces. Fluoromethane looks like this. So it's, again, mainly has one side that's non-polar, and it is mainly Okay, then you have fluoromethane, which is slightly polar, okay, because it's got this CF bond on the one side, which is a polar bond, but this other side over here is nonpolar. Okay, so this would exhibit dipole-dipole forces, which are weaker than hydrogen bonding. So make sure that you're answering the question completely. It asks you to include molecular structure, polarity, and intermolecular forces. So then your explanation part would be something like, the methanol molecules are not symmetric, so they are polar and include an OH bond. So they would have the strongest type of intermolecular force between them. Hydrogen bonding. Let me change that. The strongest type of IMF, hydrogen bonding. Making them, you could say, stick together better than Freon, which has weaker dipole-dipole forces. So it makes sense that methanol's boiling point would be higher because it would require more energy to break the intermolecular forces to turn liquid methane or methanol into a gas. So again, make sure that you're answering the question completely because I will look for it. So it asks about molecular structure. Okay, so in my explanation, I tell you that methanol is not symmetric, so that they're polar. There's my structure part, the not symmetric. And I also mention the OH bond, which wouldn't be part of the molecular structure answer. I include that makes it polar, and then talk about the specific IMF. And then Freon, I really forgot to mention to write in the structure part. So Freon is also not symmetric, making it polar, but it has weaker, even though it is polar, but then I'd come back here, but it has weaker or intermolecular forces, so that the molecules with the stronger intermolecular forces would stick together better, kind of like you saw in the evaporation station, where water took the longest to evaporate because its intermolecular forces are the strongest, versus hexane, which is a completely nonpolar molecule, so its intermolecular forces would be dipole, or would be London dispersion, which is the weakest type. So it makes sense that the methanol molecules would stay together more, stronger, and require more energy to break them apart to turn them from a liquid into a gas.